Reddy sir, good morning.
Oh, good morning. Yeah.
Sir, how is the things going in Canada?
Uh, no, things have improved. They have done a lot of vaccination now. I think it's a lot under control. Yeah.
Oh, really? Great, great.
Yeah.
So, how you manage with the temperature in Canada? I heard it will be too cold in Canada most of
No,
the times.
now it is good. Yes, it usually from December it gets cold till probably March. 4 months to 5 months. Yeah, 4 months usually. But that's okay. Life gets you get adjusted. That's how it is.
Okay, sir.
Sir,
So, by the
you
way,
were there in Vellore also.
Huh?
Yeah, you were there in VIT Vellore. VIT.
Yes. Initially, I worked in VIT Vellore for 4 years before I left for Canada. After, PhD, I worked there. Yes, I was.
Okay, sir. Okay.
Yeah.
In Canada, schools are already opened, isn't it, sir?
Yes, we started our classes on September 7th, and depending on big classes, we teach still online. Small classes, labs, tutorials, they're trying to have in person or in combination. So big classes still online. Yeah.
Okay. So the maximum strength may be some 30 or.
Yes, around 40 less. They're trying to have in person. If it is 60, 70, 80, 100, it's online.
Okay, sir.
Yeah.
Sir Rag sir, we had Reddy sir here at our campus in 2015 for ICCME15 at our Muttam campus.
Okay.
I think that time I spoke about fluidized beds. I remember fluidized bed combustion systems. Yeah.
Okay.
So there are 22, I think, right now, 22 participants.
22.
Yeah. No, they will join. It happens anywhere, any conference. Yes, I can see you now in full screen. Very nice. Yeah.
Professor Alam sir, can you hear me, sir? Welcome, sir. Our next speaker, Alam sir, has joined us.
Oh, nice. Yeah. Okay.
So shall we start, sir?
Whenever you want, because if you want to wait few minutes so that a few more will join, I am fine. As I said, 5-10 minutes, it's okay. It won't make any difference. Yeah.
Sir,
Okay.
then we will wait for 2 more minutes and we will start.
Sure.
Alam sir, can you hear me, sir?
Good morning. I hear you.
Good morning, sir. Welcome, sir.
Yeah, I am solving my PPT problem. There is a problem. It's PPT just shutting down. I'm just solving it. Yesterday it was fine. When I open in the morning, then I got.
They happen. That's how they are. There will be issues.
Vidya ma'am, shall we start?
Yes, sir.
Ready, sir? Shall we start?
Yes, sir. Go ahead. Yeah.
Yeah, Rak sir?
Yes, yes, definitely we can move.
When I is replaced by we, even illness becomes wellness. Yes, we are together again on the second day of International Conference on Computing in Mechanical Engineering 2021. Ladies and gentlemen, very good morning to you all. Myself, Sanju AC, Assistant Professor in the Department of Mechanical Engineering, SEMS School of Engineering and Technology. Now we have the start of the keynote sessions. We have a very distinguished guest here with us. I would like to invite Dr. Rag RL, convener ICCME 2021, Professor and HOD, Department of Mechanical Engineering, SEMS School of Engineering and Technology, to welcome the keynote speaker. Over to you, sir.
Thank you, sir. Am I audible?
Yes, sir, you are.
Yes, yes. Yeah.
Thank you, sir. Respected keynote speaker, Professor Dr. B.V. Reddy, other dignitaries and dear participants. A very good morning to all of you. Yesterday, we had two keynote sessions led by Dr. Gerardo Carvajal and Dr. C.B. Chopin. There was a plenary session led by Professor Dean Ushnish. Today, I am here with great enthusiasm to introduce and welcome Dr. B.V. Reddy as our keynote speaker. Professor Dr. B.V. Reddy is a professor in mechanical engineering in Faculty of Engineering and Applied Science, University of Ontario Institute of Technology, Canada. Prior to this, Dr. Reddy worked as an associate professor in mechanical engineering department, University of New Brunswick, Canada. Dr. Reddy received his MTech and PhD in mechanical engineering from IIT Kharagpur. Dr. Reddy's research interests are in the area of advanced and sustainable energy systems, exergy analysis, energy management, waste heat recovery, and alternative energy resources. He has led funded research projects in the area of energy systems. Dr. Reddy has published 160 papers in referred journals and referred conference proceedings. He is also involved in the organization of many international conferences as a chair, track chair, organizing committee member, advisory committee member, etc. He has also chaired technical sessions in international conferences and has delivered keynote and invited presentations in conferences. Dr. Reddy also contributed book chapters along with his research collaborators in energy systems area. He has also received Best Professor Award for teaching excellence 5 times, both in India and in Canada. On behalf of the organizers of the ICCME21, I extend a warm welcome to you, sir. I also welcome all the dignitaries and participants of this virtual meeting. Thank you.
Thank you, sir. Thank you, Professor Rag. And I want to thank the organizing committee members for giving this opportunity. I also want to thank Dr. Vidya Chandran, for all the communications and the enthusiasm and interest for this keynote session. Okay, so what I am going to do is I will be presenting as it is given in the conference program schedule about second law of thermodynamics and little things related to the energy systems sustainability side. Okay, yeah. So let me share my screen. Are you able to see my screen, please? Madam, can you confirm?
Yes, sir, we are able to see.
Okay,
it's good.
It's good. So I just put the video mode off. Is that fine?
No problem, sir.
Okay. So as it is said in the title, I'm going to speak about second law of thermodynamics and its role in engineering and sustainability. Okay. So before I go ahead with my keynote discussion, as I said, I would like to thank one more time the organizers and particularly Dr. Vidya Chandran and the team. Okay, so I'll give little background related to the introduction, and then the energy systems, their growth over the period of time, and what sort of environmental issues these days we talk and how to address them, and what is the role of second law of thermodynamics, and how second law of thermodynamics is gaining even much more popularity with reference to these systems, their analysis, and a little bit with sustainability, followed by conclusions. Okay, so as you see, with the exception, I know last 18 months, because of COVID, the whole globe has, suffered, or still we are trying to get through it. But in general, if you put on a global scale, always there is a demand for energy because of population growth and because of development in many countries. Okay, so the consequences are depending on what sort of energy source we use. There are going to be greenhouse gas emissions. If it is natural gas, coal, when these are oils, when these fuels are used, there are pollution associated. And this has consequences. If it is carbon dioxide, we know what impact it will have it. So there is a growing interest to utilize more and more renewable energy sources. And this way, at least we can bring down the emissions and related side of the global warming. And also it will lead to the sustainable development side. Okay, as you can see. So I'll just give little brief by taking this particular data, as you can see here. This is the energy demand growth that is 2001, which is actual data. This is the projected data. If you see here, please, it gives you generally what sort of the contribution is going to come from different energy sources. As you can see, it is a coal, oil, and natural gas still expected to drive a lot of energy. The demand that is going to be met. So we want more and more renewables to play a role. Given the way it is shown here, still coal, natural gas, and oil going to play a dominant role in meeting the energy demand. So the question is, how can we reduce the emissions, or what sort of developments are taking place in this sector? So if we see it, I'll just go over first few minutes trying to highlight sort of developments in the power plant sector. So what you are seeing here, which I don't need to discuss even, this is a steam power plant. We teach in basic thermodynamics or applied thermodynamics, its analysis and details. The point here is, it works on a modified Rankine cycle. Over the period of time, a lot of research investigations are done on this system to improve it further, so that even if it is coal operated, still when its efficiency gets improved, emissions will come down. So if we look into the research investigations that are conducted, that are still being conducted, so these are all aimed to improve the steam power plant performance. So the cycle operating conditions to operating conditions optimization or modification, advances in blade materials and their role in work output and efficiency improvement. So what you see is still research is conducted in this area using the particularly the thermodynamic knowledge to further advance them. And if we look how with time the different energy systems are being developed or advanced. So if I go to the next one, you see there's a combined cycle power generation. So maybe before I highlight the details, probably I should put what it is. So if you see here, in case of a combined cycle power generation, this is what a gas turbine cycle is. So here we have compressor systems. So the compressed air goes to a combustion chamber. So it is represented here. Typically, it's a natural gas or gaseous fuel fed. So we burn the fuel. Depending on the gas turbine type, the air fuel ratio is controlled to meet the gas turbine temperature and operating conditions requirement. So that means, so this is coupled to a generator. So when fuel is burned, the thermal energy, the gases go into the gas turbine system where mechanical energy is produced that drives the generator where power is produced. Now with time, as I said, with gas turbines becoming so much advanced, so the exhaust gases, when they are coming out of this system, the exhaust gases are at quite high temperature. So there is a way to recover waste heat from those gases to generate steam. So this HRSG stands for heat recovery steam generator, where part of the waste heat from these gases are utilized to produce steam, and that steam will go to a steam turbine system to which a generator is coupled, and that will produce power, and it will have all the steam cycle systems one has an idea from the thermodynamic knowledge. So if we observe, this is here the fuel is fed. This is where the energy input is. So power is generated using gas cycle system. Then the waste heat from the exhaust gases are utilized. Part of it is recovered to produce steam. and it is used as a working fluid to drive a steam cycle system. So together, this is what a combined cycle is. These are the ones which are growing a lot in popularity because their efficiencies are very high, given the way it is. It is a combined heat engine system. Now, if you look why they are becoming popular, because of higher over plant efficiency, and if it is a natural gas fed system, let us say, then the emissions will go down. And in many cases, the economy side is also good. So the combined cycle power plant systems are gaining more and more popularity because of their higher efficiency, which helps not only to produce, more power, but with reduced emissions. Now the question is still here, if you see, if it is natural gas fed, though we talk that it is a high efficiency system, but still there are emissions associated with the gas. How can we reduce further, or how can these systems be modified, maybe utilizing renewable sources or biomass? So that's what whether typically called hybrid systems. So if we look into the developments that are taking place in this side, this is a combined cycle system, as I showed in the previous slide. The modification that is being done here is, please observe the unit. This is a supplementary firing combustor. So here, these are compressor systems. The compressed air is coming from the compressor system before it goes into the gas turbine combustion chambers, where natural gas is fed like this. So biomass is burnt. The compressed air goes through the system here, and that way part of the heat that is released when biomass is burnt in SFC is captured by this compressed air, so its temperature will increase. Now, for a selected gas turbine configuration, that means for the set conditions here, since we are increasing the temperature of the compressed air with this operation, so that means it needs less natural gas. So, and then the whole idea is the gas turbine system will generate power where generator is coupled. Now this will go back to the SFC, and it is utilized to produce steam, and the steam cycle will run. So if you notice this one, with the previous combined cycle configuration I showed here, what is being done here is, this is modified to incorporate a SFC where biomass is burned. Depending on how much energy is going to be fed, how much energy is heat is recovered, utilized with the compressed air, the amount of natural gas that is needed is going to decrease. So that way, CO2 emissions can be reduced further. So these type of systems, there is a growing interest now. There's a lot of research being conducted, and in literature, if you see, you do find a lot of details because of their interest, or the way natural gas is now clubbed with biomass, as to reduce CO2 emissions. There are studies, as I said, considering different what you call the biomasses. So the investigations from the literature, if we look, it is shown that there is a good scope to reduce CO2 emissions. So the research that is growing now with combined cycles are not only to improve their performance, but to utilize particularly like biomass or solar energy in hybrid mode to further bring down the carbon dioxide emissions. Okay, so that is one area. So that's what leads to, if we look, current research focus in these combined cycles are a lot of them how to utilize renewable biomass or solar with them, and that's where research areas are focused now. And not only that, in many cases, how to utilize even biomass in co-firing with coal to reduce emissions. So let me show you a typical power plant configuration that could go with co-firing mode. So this is a typical boiler, in a steam power plant. Imagine it was operating 100% with coal. Now we are trying to have it in a co-firing mode by having biomass. So depending on how the ratio of the coal and biomass, whether based on the same flow rate or for a fixed heat release rate, biomass coal flow rate is adjusted such that, the conditions are met. So in whichever way it is, the thing here is by having biomass in co-firing mode in a typical boiler system of a power plant, so we can analyze and we can do all the calculations related to this side. So whether we consider a particular amount of flow rate of biomass into the boiler system, or for a fixed heat release rate, the coal and biomass flow is adjusted such that the conditions are met. So this combination helps not only to utilize biomass, but to reduce CO2 emissions. So again, as I said, this co-firing approach is becoming more and more interest given its ability to reduce emissions and to utilize biomass. There are some, as I said, there's a good amount of literature conducted, research details are available. So if we see here, this is, it gives an idea about the emissions and depending on how the biomass coal flow rate is adjusted. So as you can see, there is a tremendous amount of scope to utilize biomass in co-firing mode with coal-fired boilers in power plant systems. Thereby, we can reduce some, CO2 emissions. The next set of area in continuation, like from a basic steam power plant to combined cycle power plants to how combined cycle power generation systems can be, modified to make them in hybrid form using biomass or coal. Now, what you are seeing here is a typical IGCC. Now, a lot of research is going on in these systems. What IGCC stands for? Integrated Gasification Combined Cycle. So please let us observe. So typically, this is a gasifier. So depending on the type of gasifier, let's say coal is fed, steam or air supplied. So we are converting the coal into a gaseous form and it is cleaned. Now this gaseous fuel is taken to the gas turbine combustion chambers. So one can estimate what is the composition of the gaseous fuel, its calorific value, all these details. Now, once we have the gaseous fuel, this is the gas turbine combustion chamber where it is burned. Now this goes to a gas turbine system. This is a high pressure gas turbine system. Then it has a low pressure gas turbine system with reheat combustion system. So this is where generator is coupled. So basically, we are utilizing solid fuel, which is coal. It is converted into gaseous form. The gas is cleaned and it's burnt in the gas turbine combustion chambers. And through the turbine system, power is generated with the help of generator. Now, the exhaust gases, still they are hot at high temperature. So they could go to a heat recovery steam generator, generate steam that will drive a steam cycle. Or it can still have one more a combustor system in between to feed heat to compressed air. So depending on how many modifications or what sort of configuration that we are going to utilize, the idea here is if it is a coal, the coal is not utilized in steam power plant case, that is with a modified Rankine cycle system. The coal is gasified in a gasifier, the gas is cleaned, it goes to a gas turbine combustion system, and it drives the gas turbine cycle where power is produced first. The waste heat from the gases can be utilized in a HRSG to produce steam. That will drive a steam cycle. So basically, this is operated in a combined cycle mode. Since it is integrated, that's how the name comes, integrated gasification combined cycles. So these are, I think, now with reference to coal, the future direction is going to be, if we want to reduce emissions, we want to increase, we want to produce power with higher efficiencies because combined cycles are very efficient. This is where the direction is going to be headed. This is where a lot of scope to do research. And, there's a growing attention. Many research investigations are conducted. So this offers a great scope, a future scope, particularly to utilize coal with combined cycle power plant configuration systems. These are highlighted. There are many areas to do research, from gasification details, analysis, modeling to, considering the type of systems, not only to produce power, to produce even hydrogen, how biomass even can be utilized as a supplementary fuel. The exergy analysis, which I will be speaking about second law a little later, many things can be done. Okay, so probably I'll continue with one more before I get into the second law discussion. What you notice here is I started showing with Rankine cycle power plant system, steam power plant. Then I showed combined cycle power generation systems, their modifications utilizing biomass. Even it could be utilized, it can utilize solar energy. Then I showed co-firing systems, then went on to talk about in the last slide about IGCC, integrated gasification combined cycles. So if you notice here, as the heading says, this is a triple cycle, good amount of research is going on now in these triple cycle systems. So basically the idea is, let us say this, the one that is shown here from a research paper is based on biomass as a fuel. So this is biomass gasifier, it is gasified, it is a clean, that will, that is going to be utilized to drive, to burn in a gas turbine combustion chamber and drive a gas turbine power plant system. The waste heat will be utilized to produce steam and to drive a steam cycle system. What comes here extra is further down it is utilized with a vapor, what you call a vapor cycle. This is not steam, please. A low boiling working fluid. So to produce steam, to produce power, basically using a Kalina cycle. So we have a gas cycle, a steam cycle, and a low vapor operating cycle. So meaning is this is a triple cycle from the same fuel source. So this is where now you see a lot of research is again conducted in the literature. So from a Rankine cycle to a combined cycle systems, now research is being conducted and headed into a triple cycle power generation systems. Thermodynamically speaking, the efficiency is getting improved a lot. I know a system like this, not only thermodynamic investigations, we also need to look into economic details and many more. But as more details are understood, when economically they make, what you call meaning, they are going to come into picture. I think that is typically the developments on the power plant systems that I wanted to discuss. Now, I will be discussing about the second law and what sort of impact it is making, why second law analysis or second law discussion is gaining a lot of popularity. Why people are paying so much attention on second law. It's known, when we do for any system analysis which is based on first law, what is done is we try to make energy balance, we try to define, we try to calculate losses, efficiency. So this is how it is done, which is second law of thermodynamics. Probably in the last 30 years or so, it is being utilized a lot in analyzing engineering systems, thermal energy systems, so that I mean details can be understood in a way that helps to improve the processes or improve the whole system or the performance of the system. So that is where, if we see the second law, it brings many details into picture, a direction to a process, the role of irreversibilities, and even it tries to bring the meaning of quality, like from the energy, you know, how it is utilized. So, and will provide role of different operating conditions, again on the system performance from quality point of view, which I will be sharing some details as I go through in the next couple of slides. Okay, so there is a way to conduct this analysis. Okay, if I mean any typically these days a typical thermodynamic book will provide details on how to conduct exergy analysis or second law analysis. And in the literature, we come across a lot of research that is being done. Now, typically the procedure is, once any system is considered, let us say a thermal system or a power plant system, we go around at different states, try to calculate the availabilities and then the role of what you call the physical exergy, chemical exergy. Typically, we neglect the role of kinetic and potential effects or those exergies. So in exergy analysis, the procedure is, once we know at state points the values of enthalpies, entropies, those things, so we calculate what is the availability. Okay, so the availability could be estimated. Now we estimate what is called the physical exergy. So the physical exergy is, you know, if you take a compressor, when atmospheric air enters through it, when it gets compressed at the exit of compressor, its conditions are different. The composition is same, but conditions are different at high pressure, high temperature. So with reference to what we call the atmosphere or the dead state, it has ability to do something. So that's what the physical exergy, it could be estimated, and then the what you call the exergy associated, it could be calculated in this way. Then let us take a combustion chamber in a combined cycle system. So what is done there is air is supplied, let us say natural gas as a fuel is fed, and depending on the conditions, air fuel ratio is controlled, we burn it. So that means there we are getting into chemical exergy side of calculations. So there are many ways to calculate, you know, I mean, details are available. So the chemical exergy could be calculated using a form like this. So for a considered system, depending on the state, we calculate physical exergy, we calculate chemical exergy. As I already said, the exergy terms associated with kinetic energy and potential effects are usually small and people neglect them. So once the physical, chemical exergy terms are calculated, then the total exergy rate at each state, which is the sum of the physical and chemical, could be calculated. So the idea is calculate the exergy values at different states, calculate the total exergy, then we define the performance. When we define the performance, what is that this is going to provide? Why should we do the exergy analysis? What additional details exergy analysis will provide when we compare with energy analysis? So energy analysis, typically the first law of thermodynamics, where we make energy balances, we are not getting into the quality side of discussion. It is the second law of thermodynamics or the exergy analysis that is going to provide the quality side of the analysis and details. So how does it vary? You know, I mean, what is the role of different conditions? All these details will come only through the second law analysis. So this is just one example that gives for a combined cycle, which has many components. Let us say there are a set of operating conditions that were taken. If we analyze for a heat recovery steam generator, we are interested to see, I mean, what happens to the exergy losses and exergy destructions put together. That is through analysis. If it is done, if it is represented, we see. Now, if we want to get little more meaning of it from exergy point of view, I'll show you a particular set of data or results from research publications. Let us take this one. So what you are seeing here is, for a typical combined cycle power plant system, through exergy analysis, the exergy losses, exergy destructions, these are represented. So what you see is there are many components here, please. So there are compressor systems, there are, gas turbines, and there are other things, including condensers. Sometimes when we look at condenser in a steam power plant, we may see from energy side, oh, there is a lot of energy loss, but quality wise, from second law wise, its meaning may be very, very different. It may not be that much significant. Okay. So what you see here is the exergy, destruction, the loss for components are represented here in terms of percentage of exergy input. So what is observed here is that there are certain components. So these components are having a significant values associated. You see combustion chambers, you see the HRSG. This is where the exergy loss, the exergy, particularly if it's combustion chambers, the exergy destruction. Because you know why? If you take a main combustion chamber where we fed we supply compressed air, natural gas is fed. Maybe I can take to one of that figure quickly. Okay. So let us see here. This is the combustion chamber. Now, if we are supplying air, this is natural gas. Now, based on the type of gas turbine, we control air fuel ratio to control the operating condition, because if the blade can withstand 1300 degrees centigrade, then we have to have the products here, the gases, at a designed pressure ratio going at 1300 degrees centigrade, close to that. We are not going to feed too high. So now, when we burn air fuel ratio, when we burn the natural gas with the correct amount of air fuel, then the temperature that is associated with the products will be very high. So meaning is the air fuel ratio will be adjusted in a way to meet the gas turbine requirements. When we supply more air to bring down the temperature, which is a dilution, as we know, it is a irreversibility that contributes for entropy generation. That destroys quality. So this, if we look from first law point of view, it doesn't bring out anything. It simply makes energy balances. So we'll be taking this, we'll be making an energy balance. When we do the second law analysis or the exergy analysis, that's where we see how these different components are performing from quality point of view. That's what exactly is represented through research analysis and data here in this particular graph. So there are so many components of a combined cycle system that are considered. And if we see these combustion chambers or HRSG, they typically say that this is where in combustion chamber, there is a lot of exergy destruction, quality being destroyed, or in HRSG, there's both loss and destruction. So if we are trying to aim to improve this overall combined cycle system performance further, then probably there is a much room to improve the combustion systems, their design, the operation, And that is linked with the gas turbine blades, their advancements too. But this provides more details. Otherwise, if we just go by first law analysis, or if we go by first law calculations, basically we are not in a position to identify from quality point of view where the focus should be. Sometimes first law will tell, oh, in the condenser, there's a huge energy loss, heat loss. But quality wise, it may not be that much significant compared to what is being destroyed in a combustion chamber, or what is the exergy loss and exergy destruction associated in a heat recovery steam generator. So on this count, the second law analysis for engineering systems is gaining a lot importance, because the exergy analysis, if we go by the procedure, this is a well laid out procedure in the literature. If we go by the procedure, if it's conducted, the results will throw, or the results will provide significant amount of information and details where we can focus on certain components or processes to improve them further, and leading to further improvement in the performance. And if these are the systems utilizing, let us say, natural gas or coal, there is a room where emissions can be even brought down. Or, I mean, from second law point of view, those systems performance is being increased or improved further. So that is probably good. I mean, what you call the good amount of reasons why second law is receiving a lot of attention. So let me just bring out one more thing. We see, process heat, that is, the steam is utilized in many applications because, it is an effective medium for supplying heat. In earlier days, they used to use steam boilers to produce saturated steam, and that saturated steam used to be supplied to for process heating applications. If we just consider a boiler which was used to produce this process steam for applications, just only steam, typically saturated steam, at around 150 degrees or 200 degrees centigrade. When we look the boiler system, when we do the analysis based on the first law of thermodynamics, wise, it tells you, okay, this is what the fuel is fed, this is what the steam is coming out, these are the losses, so make energy balance, you can define efficiency. So first law will tell you, basically make energy balances, and you can estimate its performance. It's not going to say what the process type, the details are, whether it is efficient or not. Is there an alternate way to do improvement? Now, if we bring second law of thermodynamics into picture, for a such process heating plant, where if this is the boiler trying to produce saturated steam, let us say at 100 degrees or 200 degrees centigrade for process heating applications, when we burn a valuable fuel, like let us say like a coal, just to take example, when the fuel is burnt, the products are quite hot. Now we are generating steam, which is, let us say, 150 degrees centigrade or 200 degrees centigrade. So if we look at delta T between the product, the combustion products and the saturated steam that is generated inside, which goes for process heating applications, the delta T is so large. From second law point of view, that is one of the irreversibility that leads to entropy generation. So meaning is a lot of quality being destroyed. So instead of just using that as a process heating plant, if the boiler can be modified in a way to produce high pressure, high temperature, superheated steam, let the steam be utilized in a steam turbine first to produce power. Then let the conditions be set in a way that we can extract the steam to meet the process heating application. So these type of details first law will never provide. It is the second law. So I think one can talk about second law or the related side of the details. There are many applications or many cases which could be discussed. Just this one example provides a good amount of idea or details. So that is the reason why these days for many systems, whether they are thermal or energy systems, we try to do entropy generation analysis and leading to exergy analysis, which will help, as I have shown in the earlier discussion here, I mean, which components where there is a room to improve them further, so that way overall system performance can be improved, which will lead to more and more sustainable site. Because when the efficiency or performance is improved, if they are natural gas or coal operated systems, let us imagine, their emissions are going to go down. So basically they are going to become more and more sustainable. So for many engineering systems in general, it is the second law of thermodynamics. The analysis associated with second law, that's exergy analysis, if it is applied, there is a huge room not only to understand the details and a way to improve, modify those systems to improve their performance. Now, these days, we do hear a lot about sustainability. The sustainability, as I said, it depends. So anything that we do in a way that it's a more sustainable in the long run, that's what we want. So if I go back to the systems here, one of the system, okay, a combined cycle power generation system is there. Suppose this is where the focus is. Not only we analyze the components from exergy point of view, we know which components, there's a exergy destruction or more exergy loss from the components. So that way focus can be paid to those components to improve, to understand them better. Then a way to improve them, it could be related to materials. As the materials gets advanced, so these components design or their operating conditions could be modified. So the whole thing is going to be interrelated. So with the help of the second law, as more and more we understand and more research is done, so if those are natural gas or coal-fed systems, so this that exergy analysis approach will even lead to ultimately to make them more sustainable. Okay, so this is where we see in the literature good amount of research work is now focused. That could be in different ways, whether it is through power production, power plant systems, or a combination of systems where we generate power, also we generate hydrogen production. And there are many, approaches or methods that are developed and leading to sustainable indicators. If it is a complete renewable, let us say solar or wind, accounting for the material or other things that are related with those systems, generally they are, where they don't contribute for any emissions. So if we give an indicator for them, then we can have this coal or natural gas systems or the hybrid version of them. That is like if I have a combined cycle power plant where instead of natural gas only biomass is fed or solar is fed. So we converted that into a hybrid mode. How do we compare this with as if it had, if it is a, let us say, a completely a renewable type of a system. So there's a good amount of research that is being conducted now on how to come up with these sustainable indicators. And these are, there are like, based on a different set of parameters which are being developed. Okay, so energy, economy, environment. So there are publications, and particularly some of them, just I highlighted only one here. It goes on particularly for a coal-based system that involves power and hydrogen production. How can we have those indicators, and under different conditions, how to compare them with a renewable side of systems like solar or wind. So that is how the further contribution of this second law of thermodynamics is leading towards the sustainability side of the discussion or development. Okay, so I think I'm getting close to the what you call the conclusion side of the discussion now. So as I said, the advances, the research investigations on power generation systems, they are happening. A lot of research is conducted on combined cycles, combination, hybrid, IGCCs, and how to advance them. It is not just based on first law, based on the second law of thermodynamics. So still there is a lot room. We need to do further research with not only in power generation mode, in a multi energy systems. Let us see. There could be a power plant system that is generating power using combined cycle. Still, there could be room to generate hydrogen, or a multi output systems. So that will further lead to improved efficiency. And this is the big area now in terms of energy side, particularly how to have solar or biomass combined with natural gas or coal in hybrid energy systems. In power generation systems, the biggest advantage that comes is if we can utilize solar, if we can utilize biomass, let us say with a natural gas system or a coal-based power plant system, because these are large scale systems. So depending on how much solar is utilized, how much biomass is utilized, there is a room to reduce emissions. And that on one side is going to be more sustainable way of doing power generation. And by utilizing the knowledge of second law, their performance can be further improved, which will also even make them even more sustainable. See, it is good to have 100% renewable, but it is going to be a long way. So having hybrid energy systems where natural gas or coal is utilized with solar or biomass is going to make them more and more sustainable side of the development. Then, as I pointed out, is not just me. If you particularly see in the literature these days, the second law analysis or exergy analysis is the one which is gaining a lot popularity. And as I pointed out at two locations of the discussion, it is exergy analysis that will bring out more details from quality point of view. Whereas first law of thermodynamics, where we do energy balance, it will just provide what you call the energy balances, and we are not in a position to differentiate. That is where the exergy analysis or second law analysis will provide the details related to the quality, whether what is used here makes a meaning or how this component can be improved. All those things are going to come into picture. Then, though I did not put certain details in my presentation because of the time limit, there is a good room to focus on energy conservation measures, because these energy conservation measures help further to reduce the heat losses, to improve the performance, and that way we consume less fuel because we're utilizing the waste heat available before it is thrown to surroundings. So which will also make what you call the sustainable side little better. Okay, so that's what waste heat recovery and utilization ultimately leading to the sustainability side. So it is not only improving the systems, trying to do research towards hybrid energy side of the power generation systems, the energy conservation, waste heat recovery side, and applying the knowledge of the second law. All these will further help to improve their performance and make them more and more sustainable. Okay, before I think I'll open the room for any discussion. So I would like to, particularly thank Professor P.K. Nag was my guru, with whom I did both the degrees in IIT Kharagpur. I would like to thank my funding organizations, the universities, my graduate or postdoctoral students, undergraduates, research collaborators. One more time, I want to thank the research, the conference organizers for the opportunity. So before I open the door for any questions, I just want to share one more file, if it is just 5 minutes, okay? Yeah, just few minutes, please.
Yes, sir.
If I can open it, yes. So if you are wondering, how do we do the analysis? As my time was limited, I could speak only few details. There are not only many research publications are available. Suppose if this is the system, let us say, okay, this is the combined cycle system that we are interested. So what is done is, in this paper, the whole procedure is given. Start with energy analysis, go around, make combustion calculations, state point calculations, then go to exergy analysis, define the physical exergy, the chemical exergy, get all those values, define, one can define for the components all the efficiency terms based on exergy. Then a simulation program was developed based on MATLAB, then run those details and have all the parameters, affect or influence or the impact. So this particular article, if any one of you are interested, which is available, so it could be obtained, or you can see there are many such publications like that. The last thing before I stop for the discussion is, this exergy analysis, as I pointed out, is gaining more and more popularity. As I say, it brings more details from quality point of view. Okay, I think this is where I will stop. I'm happy to take any questions. Yes.
Yes, the session is open for any discussion. Any questions are welcomed. You can either unmute your mic and ask, or you can post it in the chat box. The chat box is live.
Hello, sir.
Yes, go ahead, please.
Yeah, sir. I'm Jayden from ICCME School of Engineering.
Yeah.
From automobile department. Yeah, sir, it's a wonderful session. I really enjoyed this session. But in fact, I have some clarifications or doubt about some terms. This how this exergy can be viewed physically. In fact, is it availability, or it's the quality of energy what we can expect that can be converted to some other form?
Yeah, I can clarify. Yeah. See, in the olden days, I think a few years back, they used to use in the books the availability term. Now it rewritten or went in a way that we have exergy. I will define exergy. What exergy is basically, it is the maximum theoretical work that we can obtain before a system reaches to that of surroundings or dead state. So let me take example. Just imagine we burnt natural gas with air. Let's imagine that there are combustion products at 20 bar 800 degrees centigrade. So there is a potential associated with this product. We can use it. So these products can do something till they reach that of the surroundings, which are typically 1 atmosphere 20 degrees centigrade. So exergy is basically the ability to do something till it reaches that of surroundings, which is dead state. Is that clear, please?
Yeah. Yes, sir. Yeah. So it's in fact, it's a combination of the enthalpy of the system and the entropy of the system, right?
Yeah.
All.
Yes. You see, it is till it reaches that of the dead state, the difference we can utilize. Once it reaches dead states, you see now we see the surroundings. It is 1 atmosphere, let us say 20 degrees centigrade. There is energy associated, but there is no potential. It cannot do anything. So as long as there was a potential, the difference it was able to do. Once it reaches dead state, it's like dead.
Okay, so
Yeah.
it's like it's kind of physical equilibrium, or
yeah,
or some
before it reaches. Yes, we are trying to
before it
utilize it.
Okay.
I will add one more point, I think, before you continue. Why this exergy analysis is gaining more importance is because from first law, that's what people used to do, all the analysis, calculations, and even design in the earlier years. The exergy analysis provides little more details on quality, because it doesn't differentiate. I told you, I gave you example of a process heat plant. We can generate by burning fuel. Let us say you burn it, we can generate steam at 10 bar, saturated steam. Let us say it is 150 degrees centigrade. We can use it. So first law wise, it is fine. But if you look from second law point of view, if we are generating saturated steam by burning a valuable fuel, why to do that? We can generate superheated steam, that is allowable conditions. Let us say 100 bar, 500 degrees centigrade. We can use it in a turbine first, then we can use it for process heat. So the second law tells you what is the best way to utilize that fuel energy more efficiently, which first law doesn't bring out. So I think there are many more details that goes on. Basically, it is trying to tell you which route is the best, how to utilize it. Okay.
Okay.
Yeah.
So in fact, the recent research is going towards how we can reduce this irreversibilities in these processes. Am I conclude like that, or maximum we are utilizing the maximum quality energy, reducing this irreversibilities of these processes, etc. Right?
I think very good question. What you raised is a very good point or very good question. So let me put this way, my reply. With the time, what happened is, we want to do a process in a way that there is a less entropy generation. We cannot have ideal process, that, we will never have. There will be entropy generation. So let me take example. Let me go to this. Just give me a second, please. Just give me a second. I will go. This is a classic example.
Yeah.
Take this combustor. So what is done is, this is compressed air. This is the fuel. This is the gas turbine. If you look in 1970s, let us say a gas turbine made in 70s, its operating temperature may be 800 degrees centigrade. Let us say the blades were able to withstand 700 degrees centigrade. So we used to control air fuel ratio in a way to match this requirement. And if you go by thermodynamic second law, we supply more air, we dilute more to bring down the products to 800 degrees centigrade. So that is, irreversibility is high, entropy generation is high. If you take the latest gas turbines, which operate around 1350 degrees centigrade, so that means now we are diluting less with the time, with advancement of materials. The way this is utilized, now the entropy generation is less, or the quality destruction is less. So one way the thermodynamic second law knowledge is helping. Maybe if we develop a material that will withstand this, that will improve the performance, or a improved material is utilized in a process, that way it is helping to have more, the high performance or quality destruction is less. So that is where the irreversibility or entropy generation term comes, or how it is being reduced. I think you probably got the meaning.
Yes, sir. Yes, sir. This subject, in fact, till this first law, it is purely mathematical, easy to comprehend. But when we start the second law, it become more philosophical. That is what I felt always. So I have so many doubts from that means from that point of view. That is what I asked. So this all this.
Yeah, it is. It's a very good. You know what the second law is. It tries to tell you. I mean, the how the direction will happen, what the limitation will be. Let me take another example, because you brought little bit philosophical word into discussion. I will just take little bit to take to that side of discussion. So let us take a water heater. You know water heater. So if we take a water heater, we brought water in a small container, you have a water heater, you are supplying electric power to water. What happens? The water gets heated. You agree with me?
Yeah.
Okay. Now, you were utilizing the same electric power, you are feeding it to a laptop. So the laptop was working, maybe you are able to present your PowerPoint to your students and you are discussing. So now, if we go by first law of thermodynamics, first law will tell you, you are giving the electric power to water, water was getting heated, so you just make energy balance, take into account the losses. So if it is satisfied, that means the energy balance is done. That is what first law is. So now let us bring second law. So second law tells, okay, what were you doing? We were feeding electric power to heat water. Now, if it was electric power, if we were giving to laptop will work and it will show the slides or it will show the PowerPoint. Now, if we used that power of 1 hour that we were supplying to laptop to heat water, if I take hot water next to the laptop, I will ask the laptop, please run. First law, it doesn't make any difference. It always tells you that is good. You made energy balance, that is okay. Now, second law will tell the hot water is not going to help to drive or run the laptop. So that means second law clearly tells which way or which direction things will happen. See, this is where what I am saying is, when we do more of that second law research and try to understand processes or systems or components or the whole configurations, we will find qualitative way to improve their performance further, which first law will never tell us.
Yes, yes, yeah.
Yes. Okay. This is just a few examples. There are many. Please, I think if I request Dr. Vidya Chandran, if you stop recording for 5 minutes, I can share little things with the audience. If you do that.
Yes, sir.
I don't want this to be recorded. If madam agrees, then I just want to share one thing. It's a funny thing.
Sure, sir.
No, I don't want it to be recorded because you said it's a live streaming. It's let the participant hear. But I think okay. So maybe I tell this way. Since we are getting into the first law, second law discussion, first law always talks about balances. Second law goes into quality side of discussion. Let me take the example, whether it is you, I mean, I don't know your name, please, but what you brought is very, very nice discussion. Let us take you or me as an example. We have 8 hours in a day that we are going to work or we need to work. So, I mean, let us say we were into organization and we were utilizing the time, 1 hour, maybe you were teaching or I was teaching 1 hour, we were, going around, or what I am saying is the 8 hours in a workplace, first law will say you are doing some work for 2 hours, you are reading a newspaper, you are doing this. So finally it tallies the hours and it says, oh, you were there at workplace for 8 hours. So you fulfilled the requirement. So first law wise, the balance is fine. Now let us get into second law. Second law will tell you First 2 hours, you are in the lab doing research. That is good. That's what you are supposed to do. In the third hour, if it says that, oh, you are reading a newspaper for 1 full hour, that is not what you are supposed to do in the workplace. So second law will tell what is done in the third hour is not what is supposed to be done. So second law goes into details to bring the details from quality point of view. So this is what I am telling you. That is why these days engineering systems, people are trying to analyze more from second. Okay. Yes, please. Any other questions?
Yes,
Yeah.
yes. No, sir. Yes, that's great, sir. Thank you. Thank you, sir. Thank you.
No, it's okay. Are there any other questions, please?
No questions.
No, there are other participants. I think, let me see if I can put my video mode back. Yeah. Are there any other questions, please?
Any more questions?
Okay. I think
you are very
maybe
clear, sir.
if there are no questions, I will take a minute or two, sir, just to share a few more thoughts.
Yes, sir.
The research side of it, there is a lot room. It doesn't matter whether you are into thermal system, you are into energy system, you are in general into engineering. Second law knowledge can be utilized to improve many systems further. So it doesn't need a big, what you call the equipments. It doesn't need research facility, huge research facility. It needs the knowledge of thermal, what you call side of the knowledge, and it helps when research is done. It is going to bring out a lot of details. So a lot of the participants, I know they all of them may not be only professors. There could be PhD scholars, there could be masters, or some of them could be from colleges. Whether you have facility or not, facility should not restrict you in doing some research. So that is where, like, simulation type of work or analysis based on these thermodynamics for different engineering systems, it could be conducted even with one student, and you can publish in conferences, you can publish in journals. So that way the research activity, because once you are into this side as a lecturer or a professor, we need to do research, and even with little facilities, with theoretical knowledge, research could be conducted, and that could be shared like this in these forums. So that's where I just wanted to maybe provide a little bit of suggestion and encouragement, so that research is what is needed now for us, particularly when you speak about the number of colleges and number of engineering students in India. Research should be conducted at a high level, so that it contributes for the growth and development. Okay, I think, are there any more questions?
Yes, sir.
Okay, sir. If there are no more questions, then I think before Professor, the organizers, Dr. Vidya Chandran, they speak, I would like to thank one more time for the opportunity. I know, I think it's still I enjoy. Now almost it is 12:45 here. It's close to 1 a.m. here in Canada, but it's okay. This is a little small thing that one can do back, to contribute. Yes, go ahead, madam. Now I am done from my side.
Thank you.
Yeah.
So it truly was a wonderful and informative session. We thoroughly
thank you very
enjoyed
much,
the
sir.
session,
Thank
sir.
you.
Now, may I have my pleasure to invite Mr. Joe Cheryl Dakota, Assistant Professor, Department of Mechanical Engineering, ICCME School of Engineering and Technology, to propose a word of thanks.
Thank you, Sanju. So, good evening, Professor Dr. B.V. Reddy, and good morning to all the professionals in this colloquium. It is my privilege to have been asked to propose a vote of thanks on this keynote session. I, on behalf of the AICT-sponsored 3rd International Conference on Computing in Mechanical Engineering, organized by ICCME School of Engineering and Technology. And let me call it the fraternity of researchers and scholars here together. And on my own behalf, extend a very hearty vote of thanks to Dr. Professor B.V. Reddy for sharing with us his novel observations on second law of thermodynamics and its role in the engineering sustainability. It was quite inspiring and contained all the essence to trigger the mind of a researcher to think towards developing an energy conservative, sustainable living. Thank you, sir, once again for sharing your valuable time with us. I also take this opportunity to thank each and everyone here for being a part of this conference. Thank you.
Thank you, sir.
Yeah, thank you, sir. Thank you, madam. Thank you all.
Thank you, sir.
Thank you, sir.
Yeah, bye. I know it's a morning there, it's night here. So, okay,
Sir,
thank you.
Thank you,
Bye.
sir, and good night, sir.
Good
Bye.
night, sir. Good night.
Good night, sir.
Bye.
Ladies and gentlemen, we are moving on to our fourth keynote session. Before we move to the next keynote, let me kindly request you to fill in the feedback through the link posted in the chat. Now, I would like to invite Dr. Ra Garel, convener ICCME 2021, professor and head of the Department of Mechanical Engineering, ICCME School of Engineering and Technology, to welcome the keynote speaker. Over to you, sir.
Thank you, Sanju. I think I'm audible.
Yes, you are, sir.
Okay. Respected guest, Professor Dr. Alam Mohammed Mahbub, other dignitaries and dear participants. Once again, a very good morning to all of you. With great privilege and proud, let me introduce and welcome Dr. Alam Mohammed Mahbub to this keynote session. Professor Dr. Alam Mohammed Mahbub is a professor at Shenzhen Graduate School in Harbin Institute of Technology since 2012. He worked as a senior lecturer at University of Pretoria, South Africa, research and postdoctoral fellows at Hong Kong Polytechnic University, and lecturer at Rajshahi University of Engineering and Technology, Bangladesh. He received his master's and PhD degrees from Kidamai Institute of Technology, Japan, in 2001 and 2004, all in mechanical engineering. More than 180 technical articles are authored and co-authored, including 66 journal papers, most of which have been published in the top-notch journals. He is the author of 2 books and 15 chapters in books. He has edited a special issue in Wind and Structures, an international journal, and a conference proceeding published in Research Publishing, Singapore. He has delivered 10 keynote speeches at international conferences. His research has mostly involved fluid dynamics around the single and multiple cylinders, flow-induced vibrations, fluid structure interactions, airfoil aerodynamics, renewable energy, and flow controls. He has secured a total of RMB 8 million research funding from national and international levels. Professor Alam has received a number of awards: Japan Government Scholarship for Masters and PhD Studies, Japan Society for Promotion of Science Postdoctoral Fellowship, South Africa National Research Foundation rating Promising Young Researcher Y1, Shenzhen High Level Overseas Talent, Shenzhen High Level Professional, 2015 Shenzhen Outstanding Teacher, and 2016 Hit Creative Talent Teacher. He has also received 5 Best Paper Awards from different conferences. He is an editorial board member of Wind and Structures, an international journal, and chief topic editor of Frontiers Bluff Body Aerodynamics and Fluid Structure Interactions. He has been acting as a reviewer for the top level journals, example, Journal of Fluid Mechanics, Journal of Fluids and Structures, Experiments in Fluids, Physics of Fluids, Ocean Engineering, International Journal of Heat and Fluid Flow, Journal of Sound and Vibrations, Journal of Wind Engineering and Industrial Aerodynamics. On behalf of the organizers of ICCME21, I extend a warm welcome to you, sir. I also welcome all the dignitaries and participants of this virtual meeting. Thank you all.
Thank you. First, good morning, everybody. And also, good afternoon, including good night in some places like Canada. Here in China, it is essentially good afternoon. Thank you, Professor Rag, for introducing me. That's with many more details. And also many more thanks to the conference organizer for inviting me to give a keynote talk in ICCME 2021. I also attended some of the previous ICCME conference. I went there in India. Yeah, but this is unfortunate. This time nobody can go, nobody can move. Even particularly in China, we cannot get out of China. Even I did not go to Bangladesh for 2 years because the border with Bangladesh is closed, like India. To one of my postdoc, he could not come. He went to India due to the pandemic scary, but later he could not return. Anyway, I would like to share my screen. I think you are hearing and now see my screen, right?
Yes, we can see.
Okay, good. Yeah, there are 2 videos on the right side. One is baby playing. That interesting things is that how it's getting the oscillation. Because I mostly, my main stream is flow-induced vibrations. You will see there is a toothbrush in the baby's hand. Okay, that's actually helping the baby to get the oscillation, make it easy to get the oscillation. That we call added mass. I think Ms. Chandran, Professor Chandran Vidya, she knows the added mass. So that's the toothbrush actually acting as an added mass for the baby to excite the oscillation. Similarly, when there is a body oscillating in fluid acts as a positive added mass or negative added mass, okay, to make the body light or heavy, okay. So similarly, when fish swim, it has also the added mass, but the main focus, the focus of the added mass is not here. Particularly, I'll be paying attention when the fish swim, how thrust is generated. We expect maybe the fish swims have the sinusoidal oscillation always, but in reality, it may not be the case that the fish tail have the sinusoidal oscillation. It may be the different. So this is the topic. Do aquatic animals always have the symmetric oscillation of caudal fins? Caudal fins means the tail in the tail part. So this is the outline. I will give a background. Then the experiments on live fish. Experiments on live fish actually is very difficult. I will show you. Then we move to the numerical simulation to understand the physics. I will be presenting results on symmetric oscillation. Symmetric oscillation means purely sinusoidal oscillation. And then asymmetric oscillation. Means the oscillation on the two sides of the central line may not be symmetric, like sometimes faster, another stroke is slower, something like that. Then we use two types, type 1 and type 2. Then I investigated the system of two fish, okay? How two fish, like fish is schooling, they swim, how they behave. Then finally I'll make some conclusion. Fish, now particularly the robots have been using widely around the world. Like for coastal survey, we need fish. And to make the robots, definitely we need to understand the fish swimming behavior, like aquatic animal swimming behaviors. Even in the coastal defense, we have been using robots. And even for play, like toys, robot fish have been used. And also for biomimicry purpose, robots are common. Like why there is like bird is schooling, fish is schooling, that's we need to understand why they move together. Even like land animals like buffalo or deer, they also live in group, move together. Definitely there is something. Even we'll find the human crowd. Then why do fish or bird schools? There are different things we need to understand. They do like for the social purpose, for decision making or information sharing. They live together or they meet together. And for like mating and foraging, that is another purpose. And definitely for the survival purpose, they live together. And also to survive from the predator. And when they swim, to save energy, they swim together. So here we try to understand the schooling behavior of fish from the perspective of fluid dynamics, where the flow around two swimmers involves the most genetic flow features for the real fish. We cannot use like a number of fish, so we use two representative swimmers or two fish, and we arrange in tandem or side by side and see the behavior. Thrust is most important factor for the prey-predator competition. We know we have the small fish and big fish. How small fish survive from the big fish? It is challenging, right? If you survey the literature, even we can see later, when the big fish approach the small fish, the thrust for the big fish declines, get less. On the other hand, when the big fish come close to the small fish thrust increases. I mean, the efficiency of the small fish enhances. Okay, so two things. One thing is the small fish thrust enhances and the big fish thrust decreases. So that is why the small fish can swim faster when the big fish come close to the small fish. That is the one fluid dynamic survival technique. And also we'll see here how a quick start, that is called agility, is possible to escape from a predator. And sometimes they need to get backward movement. How they do? Let's see some experiments in the literature. Godoy and Diana did an experiment in water tunnel, and they made a force oscillation of a foil. Okay, that's a foil. And they found different flow patterns depending on the oscillation frequency and the oscillation amplitude. Bill et al. Did put a D-shaped cylinder here, okay, and a dead fish, like a robot, was put in the wake. You see, the dead fish is not moving downstream; they are appearing in the wake. Sometimes moving forward, then get backward, but it's not moving away from the D-shape. So similarly, a live fish can carry a dead fish in the wake of the live fish. If they do sometimes, live fish pull the dead fish in the wake and carry somewhere. So Goodyear Dayton, when he changed the STD, that is we can say the Stahel number, or simply we can say this is the frequency. The horizontal axis is the frequency of oscillation, and the vertical axis is the amplitude. We can say the amplitude ratio, A over D, or simply you can say the amplitude. When they increase the STD and amplitude, they found different ways. The first one, when the amplitude and frequency is small, the square symbol, they got the KV wake. KV wake means Karman vortex state. Okay, Karman vortex wake, that we know for a black body. When the STD or A star was increased, like this solid square symbol, they found 2s aligned wake. That means the vortices in the wake lie on the wake center line. Okay, KV wake, we have the asymmetric wake. For the KV, like there's a lateral separation between the vortices in the wake. But for 2s aligned wake, there is no lateral separation. They all, the positive and negative vortices are on the wake center line. But for reverse Karman vortex, that is the opposite. Okay, the arrangement of vortices gets opposite, like positive vortices on the upper side and negative vortices on the lower side, just opposite to the KV. And there's when the amplitude is, or the STD is very large, the triangle symbol, then the deflected reverse Karman vortex state appears. That means the wake is deflected on a side. The oscillation is symmetric, but the wake is deflected, asymmetric, biased on the side of the wake center line. We'll see more details about this. Here we can see, okay, we did the numerical simulation with the change in STD and A star, the amplitude, again, it is the oscillation frequency Stahel number. We found a KV wake, that you see the positive vortices on the lower side and the negative vortices on the upper side. This is the general features of the KV wake. Okay. Then we found here the solid square symbol, 2s aligned wake. Okay, the vortices are on the wake center line. Reverse Karman vortex forms when the amplitude and STD is increased. Like at intermediate value of A star and STD, we found reverse Karman vortex. You see here in the video, the positive vortices go on the upper side and negative vortices go on the lower side. Then finally, at very large STD and A star, we found deflected. DS means downward slanted wake. Downward slanted. DS means downward slanted. Later, we'll use US means upward slanted wake or deflected wake. What is interesting here, this line is the drag thrust boundary. Drag thrust boundary, that means here is the thrust, and here all these flow patterns have the drag. Okay. So what is interesting here, the reverse Karman vortex wake can generate thrust. So if we can generate reverse Karman vortex, then it may produce thrust. but it is not necessarily. Definitely reverse Karman vortex with high STD and A star can generate thrust. And also, if there is a deflected reverse Karman vortex, definitely it will be thrust and there will be high thrust. If the fish swim at a constant speed, there is no acceleration. That means net thrust is 0. That means this is the borderline. This corresponds to the borderline. At the borderline, fish swims at constant speed. Okay. So that means if the fish move at a constant speed, without acceleration, that means the wake would be definitely the reverse Karman vortex state. Let's see the experiments on live fish. So we made an experimental setup here. This is the fish holding device, and we have a bar with a hinge joint on the upper side, and we put a load cell here to measure the forces created by the fish. And here we have that water tank. Okay, here is the sketch of this water tank. Since we use camera, we use a mirror to get the clear picture of the fish swimming. It's still not much clear. We'll see later. So this holding device, we use different things. First, we had the solid structure, okay, and
So you're muted, sir.
now it is fine, right?
Yes, yes.
Yeah, frequently I'm getting disconnected. I don't know how. In the last 1.5 hours, at least I got disconnected 4 times and automatically connected. That's the good things. So I use first the solid frame to hold the fish, but it was not working because when we are holding the fish using the solid structure, they don't want to move. So then I used a sponge to hold the fish to give a little comfort. Okay, like this. You see in B3, there on the upper and lower side, we have a sponge, and the black, this is the elastic cord. Okay. Then still there are something not fluently, the fish was moving. So use the whole, all the sides sponge and move the lower structure. Here we have the lower frame, but here there is not. Okay, there is not a lower frame. And sometimes in that case, the fish was always moving forward. Okay, when the front side is open, they always try to move on the front side, but sometimes not. So we try to cap the front side of the fish, okay, to cover the front side, whether it can move the backward. So we use this kind of net, okay, mosquito net, along with the foam to hold the fish. And lastly, we use the thread wire, just not the wire, flexible wire, to hold the fish fin, okay, pectoral fins like this. And you'll see that for the first case, the movement of fish, it was trying to move forward, but flame. We'll see later what is the movement of this tail fish, what they do when they need move to forward. You can see here, what are they doing? Do you think the tail movement, tail movement is sinusoidal, or sometimes one stroke is faster and another stroke is slower? Look carefully. The forward stroke and the difference between the forward and return stroke. In this case, it did not try to escape because it was held tightly, because we tried to measure the forces using the Lorentz. So we wanted to make the fish swimming, but it was not. When they know they can escape from the net or from the device, they move or swim violently. When they don't know or they feel that it cannot escape, then they keep like this. Okay, take breath. And then we use a thread to hold the fish in the pectoral fins. It was swimming like this. And let's see this video here, what happened. Okay, when it moves forward, we have the positive thrust, large positive thrust. And when it moves backward, it creates a large negative thrust, particularly for the backward movement. Then how do they move? You see, for the in the caption, you will see the forward propulsor pattern. Okay, it was moving forward. We hold the fish using our hands, and if you just give the comfortness to the fish, it can move forward or it can move forward. So we wanted to know the tail fish, I mean the caudal fin oscillation during the forward movement. What we see here for the forward movement, the tail moves faster from the large amplitude to the center. Okay, the movement from the large amplitude toward the center was faster for the forward movement. We make a plot here and we draw a graph later, you'll see. And for the backward movement, the case is opposite. For this case, it keeps the tail like this, and we found that the forward stroke is faster. The forward stroke was faster like this. Here, this one is the forward stroke, and it was faster. That means they try to push the water in the forward, and a fish itself move backward. You can see the clear picture here. For the forward motion, forward swimming, the motion from here to center line is faster, and the motion from the center line to the large amplitude is slower. We'll call this is the return stroke, and we can say this is the forward stroke. So the forward stroke is slower and the return stroke is faster for the forward movement. And for the backward movement, the case is opposite. You see, now the return stroke is slower and the forward stroke is faster. Now first we'll discuss the symmetric oscillation of the airfoil, this foil, something like this. With the Reynolds number until 200, there's totally laminar flow. So we use 2D simulation. Now we define here the definition of symbols, like CT bar means the trimean thrust. Trimean thrust. This normalization is as usual. I think it is very common. And the input power coefficient is CP bar. This is the trimean input power coefficient. And then the efficiency is the CT over CP. Then STD is the stall number based on frequency, and the D. D is the thickness of the foil, maximum thickness. Here you can see is the chord length of the foil. C, small c is the chord length. So there are three definitions of stall number. STD means thickness based stall number. STA means the amplitude based stall number, and STC means the chord length based stall number. A star is the amplitude ratio. And here we put sinusoidal oscillation like theta equals theta m sine omega t, and theta dot and angular acceleration are like this. That's the common things. Now here we'll see in the CT, instantaneous CT and instantaneous power coefficient. During the oscillation, how the CT changes or the CP changes, we can understand from here. Here we put for three different STA value, a small amplitude, or that we call the STA, the combination of frequency and amplitude we defined before. For three different STA value, you see here. Higher STA have the higher maximum thrust and also the minimum as well, but the time in thrust is larger at higher STA. Then from like, if you see the omega t, this is from 0 to pi, 0 to pi by 2, this is the forward stroke. 0 means the work center line, foil at work center line. So 0 to pi by 2, this is the maximum amplitude. Then again work center line, okay, minimum 0 amplitude, then negative amplitude, and again the max. What you see here, sorry. In the forward stroke, you see we have the negative CT. We have the negative CT, but we have the positive power. That means we need positive power, but still at the at the initial stage of the forward stroke, we need input power, but the CT is negative. Okay. Here we have when up to 5 or 90 degree. You see here up to here. Here we have the negative CP, but still CT is growing. CT is growing. Okay. At maximum amplitude 5/2, CT is positive, and that CP power coefficient is negative. Interestingly, maximum thrust happens when the foil tends to return from its maximum amplitude. Okay, it is just slightly beyond the 5/2. That means when the foil tends to return from its extreme position. And in that case, definitely power is also going to be positive. Similarly, what the things to memorize or understand is that when foils tend to return, thrust is maximum. Okay, that thrust is maximum. If we get the curvature of the CP, del d square CP over d omega t square, that we can simply say the curvature of the CP. What we see here, when the curvature of CP is 0, we found minimum CT. CT is negative. Again, at another curvature 0, we found the maximum CT. So that's that when the CP is changing its sign, that means del square, this is the, like we can say, the gradient of slope. Del d square CP over d, this is the gradient of slope. When the gradient of slope is changing sign, like from positive to negative, we have had the largest CT. We can simply explain it here. You see here in the sketch. When the foil is at the minimum position, so not the minimum, 0 position, 0 amplitude, work center line, we have just before it, we have the maximum CP. slightly before it, we have the maximum city. And slightly after it, we have the minimum city. Okay. When it is maximum, when the foil is at maximum, after before it, we have the minimum CP. And when it tends to return, we have the maximum CT. CT is maximum when the foil tends to return from its extreme position. Now we'll see the dependence of thrust power efficiency on the STD and A star. Like how the A star, how the CP or CT changes with changing A star and STD. Here you can see these things. First is the CP. With increasing STD and A star, CP is increasing continuously. This dash line is the drag thrust boundary. Okay, this is the drag thrust boundary. CT also increasing accordingly, following the increase of STD and A star. What you see here, efficiency also getting better with increasing and STD. Efficiency increasing, but if you see the rate of thrust increase with rate of power input. Rate of thrust increase with, definitely if you give the power input, the thrust will be large. That is the conventional case. Everybody will understand. But the rate of power input and rate of thrust is important things. Okay. So DCT over DCP, you will see here we have the maximum, like STD about 0.25, and it is almost independent of the amplitude. So the biological scientists found that the aquatic animal have STD about 0.25. The oscillation, their oscillation frequency oscillation stall number is 0.25. They found from the physical observation of the aquatic animal. But this proves from the gradient of CT with the CP gives, that is why perhaps they use this stall number. Then we did some mathematical analysis of the why, like the power, we need power, more power input when we increase A star and STD, why we are getting the CT with increasing STD and A star. So we did some mathematical analysis. We can assume that this is the hydrofoil, like a flat plate, is oscillating, okay, sinusoidally. Then we can assume, though the foil is submerged in the fluid, we can assume the some like an added mass, like this kind of, this element of fluid is actively moving with the foil. Or we can say this is the equivalent amount of fluid that play a role on the foil dynamics. Okay, so we use wave-safe fluid. If we assume this fluid is moving with the foil, then it has different kind of acceleration. Because the foil has acceleration, foil has Euler acceleration. If the fluid is attached on the foil, then definitely we have also the centrifugal acceleration on the fluid. And also we have the correlative acceleration because the fluid has lateral movement and also along the foil movement, like the streamoid movement of the fluid. So we have three kind of acceleration, and these three acceleration have contribution to different parameters. Here we'll see. Consider this the elemental mass. DMF is this one, like this one, and we have the Euler acceleration or also centrifugal acceleration like this. Then we have the mass moment of inertia of this elemental fluid is this. This is already published in the paper. So if you have any question or lack of understanding, you can refer to this paper. Then the fluid acceleration and velocity is this. So torque, how the torque is mainly related to power input. Torque is mainly related to power input, and it is connected to Euler acceleration and Coriolis acceleration. So the Euler acceleration, and if we consider the Coriolis acceleration, this is the Coriolis acceleration and the Euler acceleration times like inertia, corresponding fluid mass moment of inertia. Then we found the torque involved. And for the thrust cases, definitely when the fluid is moving, we have the centrifugal force on the fluid, like fluid moving along the foil. Then we have the thrust generation. For this thrust generation, we found that's the final form. The CT is function of ST cube over STC. This is the CD0 is the drag on the non-oscillating foil. That means fixed foil. CD bar 0 is actually the drag on the fixed foil. So CT must overcome CD0 to get the absolute thrust. So from this analysis, we found the CT varied with cube of STA. Okay, later we'll see. And the simplification of the power equation, we found this is the final form of power equation, and we found the CP is proportional to STA cube. Now let's see, this is the mathematical analysis results or the equation. We'll see, again we see the efficiency is inversely proportional to the STA cube. Now later we'll see here the real data, okay, how they behave. So we accumulated all data, possible data here, and plot as a CT versus ST cube over STC, when we found the linear function. This is our essentially what we found here. CT is, if you consider this is the fixed value, okay, it is constant, then we can say CT bar is proportional to STA cube. STC is very small or more or less constant. So CT is proportional to STA cube. You see here, here we found CT is proportional to ST cube over STC. And we have proved mathematically that CT bar is proportional to ST cube. All data converge on this line. That means our mathematical analysis or the model is agreeing with the data from the literature. Similarly, efficiency does the same. Okay, does the same. There's efficiency is inversely proportional to the ST cube. Now, asymmetric oscillation. Previously, it was the symmetric oscillation, sinusoidal oscillation. But in the experimental observation, we found different kind of oscillation, asymmetric oscillation. Sometimes forward stroke is faster, sometimes slower stroke is faster, depending on their turn or their movement. So the objective is to investigate the effect of asymmetric oscillation on drag thrust boundary, providing a scaling law for estimating drag thrust boundary, and classifying the weight patterns, okay, and finding the inherent relationship between hydrodynamic force and flow structure. What we did here, did the numerical simulation. Here is the this is the conventional things. Just to remember, this is the thickness of the foil, and the amplitude peak to peak is the amplitude. Then this is the oscillation time. Here we did, you see the theta over theta 0, this is the negative and this is the positive, means this is the lower extreme and here is the upper extreme. So in this type 1 oscillation, how it is asymmetry comes from, this one is the sinusoidal symmetric oscillation. When S equals 0.5, this is the equation, okay, the kinematics of the coil, this equation can be like when S equals 0.5, then it will be sinusoidal oscillation. Okay, sinusoidal oscillation means like a symmetric oscillation. When S equal like 0.2, then you see from lower extreme to upper extreme, from the lower extreme to upper extreme is faster. You see, it's faster. Then upper extreme to lower extreme, okay, that is the slower. So changing the S, like when S equals 0.5, then we have, 0.8, then you see the from lower to upper extreme, the motion is slower. And from the upper extreme to the lower extreme, the motion is faster. Okay, so with changing the S, we can modify the shape of oscillation. Definitely this one and this one is opposite, except the upper and lower oscillation swapping each other. This is the map, okay, for the symmetric oscillation. For the symmetric oscillation, let's see. Here, just this is the baseline, because the next will be the for the asymmetric, next graph will be for the asymmetric oscillation. So just need to remember, this is the drag thrust boundary. This is the drag thrust boundary. This is the slanted wake boundary. Okay. And the plus symbol corresponds to the reverse Kalman vortex. Okay. So the drag thrust boundary lies in the reverse Kalman vortex region. This is for the asymmetric flow map. Okay. Again, this is the AD or the A star. The horizontal axis is the STD. The blue line, this dashed blue line, is for the symmetric drag thrust boundary. Symmetric oscillation drag thrust boundary. Here we can say S equals 0.4, 0.3, 0.2, and this is 0.6, 0.7, 0.8. S equals 0.5 means this one. Okay, we forward it. Now 0.4 means close to 0.5. Then you see the new drag thrust boundary is close to the symmetric one. Okay, if we decrease the S, then the drag thrust boundary moves closer to the origin. The lateral separation increases. Then what we understand, for the asymmetric oscillation, the drag can be generated with smaller amplitude and smaller STD. That means at a smaller STD and a smaller AD, for the asymmetric oscillation can give you a higher thrust. If we decrease it to S over 0.2, you see it moves further towards the small amplitude and small STD. Okay, the separation. That means the asymmetric oscillation is more effective to generate the thrust. It's easier for their swimming. What you will understand, that S over 0.5 and 0.6 essentially the same. Okay, except the here the DS reverse Kalman vortex state. DS means downward slanted, and this is the upward slanted. Okay, for this case, upward or downward slanted, it depends on the initiation of file oscillation. Okay, if the file oscillation initiates from the upward, then we will have the downward slanted waves like opposite, and the vice versa. So this one and this one essentially same. So if you consider S minus 0.5 absolute value, then this column is 0.1, this column is 0.2, this column is 0.3. So we go and say this is the asymmetry parameter. This S minus 0.5, the absolute value, it gives the asymmetry. If this is large, that means asymmetry of the oscillation is large. Then here we can see the plot of drag thrust boundary for different values of asymmetry. Asymmetry 0 means sinusoidal. You see the drag thrust boundary. With increasing asymmetry, the drag thrust boundary moving toward the small STD and AD. Okay. So larger asymmetry gives a larger thrust, and we got a scaling law here. The data collapsed like a STS. This is the asymmetry cases STA plus STA 0.05. If we get, then they all data collapse to a single line. Then why you'll be saying why their CT thrust increasing? Okay, let's see the stroke-wise thrust and power, and also the CL, the lift coefficient. This is the stroke-wise, the faster stroke. Okay, so equals 0.2. For the faster stroke, if you see the variation is large. Okay, from positive, and this is the slower stroke. The variation of CT is small. If you consider that time mean in the faster stroke and slower stroke, time mean thrust in forward stroke, if you see it's like this, that means bigger than the slower stroke. Slower stroke looks negative. Okay, so mainly the faster stroke causing the thrust to be positive or increasing. Here, this is the same phenomena was observed for different asymmetry parameters. When the asymmetry parameter is 0, definitely it is the sinusoidal. The forward and faster and slower stroke are same. Then we've plot the thrust and also power for the FS means slower stroke, faster stroke, and SS means slower stroke. So the time in thrust in the faster stroke is always larger. It makes the whole time in CT bigger with decreasing S. Similarly, CL and also the efficiency, it is the same. The forward stroke efficiency is larger. Then what happened in fluid dynamics? Here you see the U bar is the UR bar. That is the relative velocity. Okay, with respect to the free stream flow. With respect to the free stream flow, that means UR equal U bar minus capital U. Capital U is the free stream flow. Okay, that is the relative velocity. So when we have the S equal 0.5, that means symmetric oscillation. You see on the upper and lower side, relative velocity is same. And here we have negative velocity. That means this actually corresponds to the drag region. If we increase the STD, like here STD 0.18, STD 0. Third column is STD 0.17. This is the increasing STD. Okay, this is the increasing the S, the vertical column. So here you'll see that's with increasing STD, we have the positive velocity like a jet in the wake. This jet is actually responsible for making the large thrust, positive thrust. And for the symmetric oscillation, here we have the upper side, lower side maximum is the same relative velocity. But for the deflected wake, okay, or slanted wake, if you see they are different. On the upper side is smaller than the lower side when the wake is deflected or slanted downward. But for the asymmetric foil, you see here now, S over 0.06, that means actually the downward stroke is faster. And you see here, you find the now on the upper side, UR is larger than the lower side UR. And you will find the same observation But for the slanted wake, it is now different. Here you see on the upper side larger and smaller in the lower side, but it's opposite. When the slanted in the lower side, it's getting larger here. Though here and here it is the same. If the jet slants downward, then we have the lower side UR is higher. Similar observation was also made for 0.7. Now we can give a brief sketch to summarize the observation just we will find before. If the downward stroke is faster, downstroke is faster, then we'll have higher UR on the upper side. Okay, and the opposite is true. If the slant wake or the jet slant downward, then we'll have the lower side higher UR. If the jet slants upward, then we'll have the upper side. That means the higher UR and jet slant direction will be on the same side. Now asymmetric oscillation type 2. Now it is different. Now it is stroke wise. Now if you see here, from here to maximum, this is the forward stroke, and maximum to the mean with the retract stroke. So forward and retract stroke is different, faster and slower. Previously, it was the downstroke and upstroke was different, has the different velocity. Now, the forward stroke and retract stroke are different. So this one is similar to this one. Now, and this one is similar to that one. Again, we define tau is the ratio. We can say this is the asymmetric parameter. Tau, we can say that T1 over 4 over T over 4. That means T1 over T. That gives again the how much forward stroke is faster than the return stroke. So this tau gives that the ratio. Then again we see for different values of T, tau, you can see the kinematics or the trajectory of the foil. For T equal 1, it is symmetric, sinusoidal. For T equal 1, the oscillation is symmetric, purely sinusoidal. But for like a small t, less than 0.1 means 0.8, then we have the forward stroke faster. We have the forward stroke faster. And the return stroke is slower. Similarly, at tau equal 1.2, you see the forward stroke is slower and the return stroke is faster. So I believe you have understood the difference between the type 1 and type 2 asymmetric oscillations. This is the polar plot or the phase plot of the CT and CP. Okay, and you see that's the red line corresponds to the thrust and the blue line corresponds to the CP, and the solid black line is the phase portrait. That means the relationship between velocity and displacement. So this is the phase portrait of the oscillation. This is the CT and this is the CP. Tau equal 1 means symmetric oscillation. That we know, we have explained already, and we found when the foil tends to return from its maximum, means theta equal 90 degree, we have the maximum thrust, means here the maximum thrust, and here is the maximum power. If we decrease the tau value like 0.9, what we see now, this maximum thrust point is now at here. Okay, thrust point is now at here, and the maximum power is now at here. With further decreasing tau like 0.9, you see it's moving right. CP moving towards the right, like in the first like in the forward stroke, and this is the return stroke. Now the maximum CP lies in the forward stroke, and now the CP, maximum CP is on in the forward stroke. And you see now, see the difference between here and here. Now it's moving towards the still the forward stroke, and this one is moving. So now here the asymmetry getting bigger here, and the maximum thrust position or the maximum CP position is changing. When tau is large, what happened? It happens the oppositely. Here it was maximum, now it is moving towards the return stroke. This is the return stroke, this is the forward stroke. At the extreme asymmetry like tau equal 1.4, you see the maximum CT is here. So you see the difference from here to here. Okay, now both CP and CT are in the forward return stroke. This we can explain here. Here we have seen there are different things. Okay, sometimes CP and CT both are positive, sometimes are negative. There are different 4 scenarios. 4 scenarios are CP is positive, means giving power input, we are getting the CT negative. That we don't expect. Okay, we are giving the power input, but CT is negative. That means the drag. So this is the undesirable condition. When CP is large, giving the input, we are getting the thrust that we expect. So it will be the normal swimming. And when CP is negative and CT is positive, that looks not the case, real case. No power input, like negative power input, but getting thrust. That is the ideal case. And the floating is CP and CT both are negative. This is the Rose diagram for this condition, how it's changing. This is for tau equal 1, tau 0.8, and with increasing tau. What you see here, when tau equal 1, the asymmetry is large, we have the normal swimming condition very strong. Both CP and CP lying in the retract stroke or return stroke, and that is the faster stroke. Opposite will happen at smaller tau. Here you can see the quantitative magnitude of CT, CP, and efficiency with tau. You see, tau equal 1 means the symmetric condition, symmetric oscillation. When the asymmetry is large with tau, then you see we have the higher CT, also a higher power. Okay, and you see the efficiency is definitely large. Okay, for all the asymmetric cases, particularly up to here. This could be understood from the steepest ascent diagram that we approach efficiency about 0.1.5 for different lines, different cases. And this actually the optimum STD and tau with for the different cases with red efficiency, high efficiency. Then I'll give you a brief introduction of 2 P's. So we use 2 P's for the phase schooling, giving the symmetric oscillation or in phase oscillation phi equals 0. I will close sometimes, I think pushing. 2 foil oscillating in the same direction and opposite direction. 2 foil moving like this and 2 foils moving like this. This is the antiphase and this is the in-phase oscillation. You see here, CT0 means a single foil oscillation. So we are comparing with the single foil oscillation, and the CT bar is now 2 foil oscillation. This is for in-phase oscillation and this is for anti-phase oscillation, the 2 foil. You see the in-phase oscillation has higher thrust. S is the separation between the 2 foil. S is the separation between the 2 foil in side by side. We see the anti-phase oscillation has higher thrust. and also require definitely higher power input. Now you see the efficiency is large for the antiphase oscillation. That means if two or more phase swim together, they will have antiphase oscillation. Okay, the two side by side phase will have antiphase oscillation. Here is the wake structure for the two cases. This is the antiphase oscillation, interphase. From the wake structure, you can see we have a strong Z for the antiphase oscillation. Then this is the case for inline tandem foil. Okay, this is for the tandem foil. This was for the side-by-side foil. So for the tandem foil, again, CPU and CPD, U means upstream, D means downstream, in phase and antiphase. Now the case is opposite. You see now the in-phase oscillation have higher power and also higher thrust. So two inline phase, okay, one phase lying in the wake, then they both will swim in antiphase, in-phase fashion. That will give them a comfortable with higher thrust. Here is the wake structure for the in-phase and antiphase oscillation. So if we case the total performance for the tandem foils, we see again the in-phase has higher CP. Total means upstream and downstream phase, okay, for both cases, total CP. Then we see the total thrust is, power is higher for in-phase oscillation. Also CT is higher for the in-phase oscillation. But the efficiency is not the case, okay? Efficiency is the opposite. So if we make the conclusion, the instantaneous thrust is maximum at inflection point of power. Thrust is maximum near the extreme position, okay? Just when it tends to return. More power is required to move the hydrofoil from the extreme to the main than the other way around. And we found mathematically this scaling law, and this scaling law fits with the experimental and numerical data. And side-by-side foils, the antiphase oscillation gives more thrust and also the efficiency. Tandem foils, the upstream foil has more efficiency than the downstream foil, and the overall in-phase give the more thrust. Thank you very much for your kind attention and patience.
Thank you, sir. The session is open for any discussion. Participants, if you have any queries, please unmute and ask, or you could post in the chat box. The chat box is live. I invite Dr. Mahesha Rangaraj, Professor, Department of Mechanical Engineering, SCMS School of Engineering and Technology, to propose a word of thanks. Sir, over to you.
Good morning, Professor Dr. Alam Mohammed.
Good morning. Good morning.
And all the technical fraternity of this forum. It's my privilege that I have been deemed this opportunity to propose vote of thanks on this keynote session. I, on behalf of AICT, sponsored International Conference on Computing and Mechanical Engineering, organized by SCM School of Engineering and Technology. Let me call it a conglomeration of researchers and scholars here together. And on my own behalf, extend an very hearty vote of thanks to the Professor Dr. Alam Mahbub. Thank you, sir, for being with us. And you're sharing the knowledge on the topic, do aquatic animals have symmetric oscillations of caudal fin? A quite inspiring talk on emulating the nature that catalyzes the researcher's mind towards bioemulation in the application form. Thank you, sir, once again for your very favorite talk and favorite and informative talk. And I also take this opportunity to thank each and every one of the people here for being with us and being part of this conference. Thank you, sir, once again. Thank you.
Thank you very much.
Thank you, Dr. Mahesh Rangaraj. Before we stand out, let me kindly remind you to fill in the feedback through the link posted in the chat. Ladies and gentlemen, we come to the end of the day 2 keynote sessions. Now we have the parallel technical sessions 3 going on. The parallel technical sessions 4 and Numika workshop will commence from 1:30 p.m. to 2:30 p.m. as well. All participants are requested to join the respective link received through your registered mail. Tomorrow, we have the keynote 5 by Professor Dr. Arul Prakash, Professor, Department of Applied Mechanics, IIT Madras, and keynote 6 by Professor Dr. Shekharam, Professor and Principal, AAA College of Engineering and Technology, Tamil Nadu. Thank you.
Alam sir, thank you, sir, for coming and joining us.
Yeah, that's my pleasure.
Thank you. And it was exceptional talk, sir. I have a lot of things to learn from that. It's really great.
Yeah, that's good. Yeah, we can have a future collaboration.
Thank you, sir. Thank you so much, and I'm really looking forward to that. Thank you, sir.
Thank you.
Once again, I request the participants to kindly fill in the feedback through the link posted in the chat. I remind, please fill in the feedback through the link posted in the chat. Thank you.